Okay. How is everyone today? Everybody doing good? We will wait for a couple more people to join and then we will start. Okay, so any questions over anything? Okay, any questions over anything that we have done? Okay, so yeah, did somebody have a question?
Yeah, have we completed 4.1?
We are still, okay. Today we're still going to go over 4.1, so we're not done yet. That's the short answer.
Okay.
So yeah, no, we're not done with 4.1, not yet. Okay, any other questions? Oh, and this is my plan, okay? For exam number 2, I'm thinking about giving it at the end of the month. Okay? And that's just my type of thing that I like to do, is basically at the end of every month. I mean, I think the semester is what, 4 months or something like that? Anyway, but the first month you're just getting warmed up. Basically at the end of the month, I like to give my exams because then everyone kind of knows when it's going to happen, okay? So I'm thinking at the end of the month, give exam 2. It'll be just like exam number 1. It'll be a take home. You get to work on it, and then you just email it to me. And then at the end of November, okay, at the end of November, there will be another exam, and I think that will be the final exam. And I would be giving it like a little bit early because, you know, you need time to work on it. You need time to work on it, and I think the semester ends like 1 or 2 weeks after that. You know, in December. It's like the first or second week of December or something. So basically, I think exam 2 I'll be giving at the end of this month, and then exam 3 I'll be giving at the end of November, and then we basically just try to wrap things up, you know, early December. So that's my plan there for the exams. But the exams will only cover what we've covered, okay? So exam 2 will only cover after material. Okay, so it's only the new material, okay? Only the new material I'll be putting on there. Okay, so we're going to get started. So any other questions before we get started? How is everybody else's classes going? Do you have more than one class, or is this it, or? So sometimes certain semesters are easy, sometimes they're difficult, just depends on what classes you're taking. Okay, and let me set up that folder. I have a folder that I post all of my notes to. Set that up. Oh no, I already set that up. Okay. All right, so let's get started, okay? Okay, so last time we talked about this, okay? I'm going to write it one more time, and we're going to go over this a little bit more because this is, it's very easy to get confused on this, okay? I think the first time I looked at it, I was confused. The second time I looked at it, I was confused. And just in general, if you're doing math, okay, if you are doing math and you're confused on something, like, it's okay, okay? I don't know if anybody's ever told you that. There have been ideas and concepts that have been presented to me, and I didn't get it the first time or the second time. You know, it took months and months or even years to fully understand things. And there's different levels of understanding, okay? I'll just go on a quick rant right here, and then I'll get to the problem. There's different levels of understanding. There's one level where you know how to do the problem, but you really don't understand it. Then there's another level of understanding where you can explain how to do the problem to somebody else. But then there's even deeper levels of understanding where you know the proof behind the concept. Or you can use the proof to solve other proofs. There's lots of different levels, okay? So if you are presented with something and it doesn't make sense, you know, don't panic. Just keep on working at it, okay? So we talked about this equation last time, right? Okay. This backwards E, that means there exists, okay? So there exists some type of C1, C2, Cn, not all zero. Then, what do we classify this, okay? If we can find C1, C2, Cn that are not all zero, then what can we say about the functions that satisfy this equation? Okay? Is this, I want someone to say in the chat, is this linearly independent or dependent based on the definition? So help me figure out the rest of this, okay? Fill in the blank, okay? I'm drawing a blank here. So you have these constants and you have these functions, and you're trying to solve for C values, and if they're not all zero, then what can we say about this set of functions? They're linearly independent or dependent? Somebody say it in the somebody in the chat say something. Okay, so I got an answer. Okay, the correct answer is linear dependent. Okay. So, and this is the weird thing. It says not all zero, okay? So if all of the C's are zero, and that's the only way to make this solution true, so if all C's are zero, then the set is linear independent. Okay, so if not all of the C's are zero, linear dependent. If all the C's are zero, then it's linear independent. Okay, and we are going to do some more problems on this. Okay, we're gonna work some more stuff out. Okay, so what if I did this? I have f1 x squared, and then I have f2 equals negative 3x squared, okay? We're going to show, okay, show either linear independent or linear dependent. Okay, we're going to show one or the other. Okay, so this is how you do it. Okay, you say C1 times the first function plus C2 times the second function. Okay, and now you're trying to solve for C's. Okay, solve for C1 and C2 such that the equation is true. It's 0 equals 0. Okay, so here's the thing. I want you guys in the chat to tell me what values for C1 and C2 can we pick such that this equation holds true. It's 0 equals 0. So I'll give you just a minute and try to think of something. And I think there's more than one solution, okay? I think you can come up with all kinds of stuff, but the only thing that matters is that if the C's are 0 or not 0, okay? So sit down, think about this for a minute, try to find C1 and C2 such that this whole equation is 0 equals 0. And then tell me what you get. So the C's are just constants. You pick any constants you want. So it's like a little puzzle game. Okay, so any responses for C1 and C2 to make this 0? Can anybody think of anything? And you can't just pick 0 for C1 and C2 without having to try to pick other values. Okay, somebody said pick one for both. I don't think that would work. Okay, so here we go. Yeah, okay, so 1 and 3, right? Yes, yeah. Okay, so watch this. And again, there's more than one solution, okay? What if we did this, okay? What if I said C1 is equal to 3 and C2 is equal to 1, okay? So if I pick these numbers and I plug them in, I get 3x squared minus 3x squared equals 0, and this implies 0 equals 0, okay? And this is what you get at. You may get 0 equals 0, or at least try to get this. If you get this, does that mean it's linear independent or dependent? The fact that we picked two C's and then got 0 equals 0. It means dependent, okay? Remember, the only time that it's independent is if all of the C's are 0. If those are the only values that make that satisfy this equation right here, okay? And also remember from last time, look at the functions, okay? We already know they're linear dependent because one function is just a constant multiple of another, right? One function is a multiple of another, so it's automatically dependent. This is just another way to show a dependent. Okay, great. All right, we're going to do a couple more. Okay, I'm going to erase this. Okay, this is the same deal right here. Same deal. We have f1 equals 2 to the x plus 3, And then we have f2 equals 2 to the x, okay? So we're looking for, if you want to show linear dependent or linear independent, okay? So we have C1 times 2 to the x plus 3 plus C2 to the 2x equals 0. Okay, so find C1 and C2 such that we get 0 equals 0. Okay, so I'm going to give this problem to you guys, and I want you to think about this for just a minute and see if I'll give you, 1 or 2 minutes, see if you can come up with C values such that this is true. Okay, so go for it. Okay, anything for C1, C2? Any ideas? Or do you have any ideas on how to even start? Well, I will give you a hint, okay? So are you guys still working or stuck or what? I'm sure there's like 8 people in this class. I'm sure somebody can get something. At least something. At least something. We can use powers, right? I mean, well, okay. Yeah, what do you mean by powers? Because I can say, whatchamacallit, 3 squared is equal to 9. I could write 9 or 3 squared. It's the same number, just a different representation of the number. Okay, I'm going to do it. Hopefully, if you worked on it, you might get something similar to what I get. Your answer might vary, but it's the same idea. Okay, how about we split this up, okay? How about we split this up? Because this is a part of this, right? Okay? Remember, there's that rule that says that if you have the addition of 2 different exponents, that's really just the same function multiplied by itself. Kind of just gave away there. It's the same function multiplied. It's 2 bases being multiplied to each other, okay? All right, great. Okay, so now we have this. We have C1, we have 8, we have 2 to the x, plus C2 to the x, right? Okay, well, all I have to do is set C1 equal to 1 and C2 equal to -8. And then if I plug these in, right, I get 8 to the x plus -8 to the x equals 0, which in turn shows that both sides are equal to 0. So you're just trying to figure out how can you make both of these cancel each other, okay? And I will say this, is that when there's only 2 functions, it's not that bad. But if it's more than 2, then it's a little bit more complicated. So we conclude linear dependent because one function is a constant multiple of another, okay? So what's really interesting is 2 to the x and 2 to the x plus 3, that x plus 3 is just, the plus 3 is just another constant multiple of the same function, which is really, really weird if you think about it. So you have some exponent, and you're adding something in the exponent, but really that's a multiplication in front of the function. That's weird. Anyway, but it's true. Okay, I'm going to save this slide, and then we will do some more.
So you said we can have different answers on this, correct?
Yeah. For example, okay, watch this. Okay, watch this.
So I was going to use 1 and 3 to the 1 power or something like that, or 1 to the
Okay.
1 to the 3 power for C2.
Okay, watch this. Okay, I'm going to do the same problem, and I'm going to try to get different C values. Okay. So how about for C1, I pick 1 over 8. Okay. If I pick 1 over 8 for C1, that'll make this term right here just 1. And then if I pick C2 as -1, I think it works out. So what will end up happening is when I plug in 1/8 into here, I will just get 2 to the x. And then if I plug in -1 for C2, I'll get -2 to the x. And it turns out that that ends up working. So, and if you look here, there's a relationship. I have 1 over 8, -1, but then over here I have -8 and 1. It looks like it's an inverse, it looks like the relationship, at least in this case, and anyway, it'll depend on each case. But the whole thing is that we found different C values, right? You can do it multiple ways as long as it works out.
Okay.
So whatever C values you pick, just as long as it works out, then it's okay. So okay, so we will do another one. Okay, so what if I have this? Okay, f1, okay, is e to the x. Then I have another function, and this is ln x. Okay, so we have c1 e to the x plus c2 ln x equals to 0. And it's show if it's linear independent or linear dependent. Okay, so try to find C1 and C2 that works. If that connection is lagging out, just jump right back in. No worries. Okay, so C1 and C2. Can anybody think of anything? Okay, so here's the deal, okay? Remember, for linear dependent, it's all about one function a constant multiple of another, okay? But the thing is that in this particular situation, e to the x and ln x, these functions are not a multiplication of each other, okay? So in this particular situation, if we let C equals 0, or C1 equals 0, C2 equals 0, we will have 0 plus 0 equals 0, okay? And remember, if all C's are 0, and that's the only solution, and it's the only solution, then it's linear independent, okay? So in the other two examples, we were able to say they're constant multiples of each other. In this one, they're not, so linear
I
independent.
thought e to the 0 is 1.
Oh, okay, so here's the thing. We're not plugging in 0 for x. We're plugging in 0 for C1 and C2. So
Okay, never mind.
it is true that e to the 0 is 1, but the thing is that's when x equals 1. We're trying to solve for C1 and C2 here, okay? Okay, so here's another question for you guys. And the other question is this
Well,
the only
I
way?
have a question on this.
Yeah.
So, I mean, this is a little subjective, these problems, because it's like if you try you're asking, it seems like these problems are asking people to be a human computer and try and solve for C1 and C2. So, I mean, if all else fails, you put in 0 and 0. But I mean, what happens if that's not right? Then what?
Well, okay. Okay. So so here's the thing. So yeah, this is kind of tricky, right? Okay.
I don't
Let
think
me
it's
tell you
tricky.
this.
I just whoever came up with this concept is, oh my God. Yeah.
Okay. So the whole thing is this, okay? The whole thing is that you have to know your functions, right? Know your functions. If you see that two functions are a constant multiple of each other, then it's going to be linearly dependent and you try to solve for the c values. If the functions have no relationship with each other, odds are there's an indication that it's probably going to be linear independent, right? Okay. E to the x, okay, so here's the thing, without even solving for c, like who cares about solving for c? E to the x and ln x, these are not related to each other by a constant multiple, so odds are it's probably going to be linear independent unless something else happens and you know, and unless a miracle happens and it ends up being true. But the whole thing is just look at the functions. Are they related to each other by a constant multiple? In this case, they're not, okay? So that's the whole idea here, okay? And here's the whole thing. Remember, this is not the only way, right? This is not the only way. Okay, this is just one way to show.
Yeah, that's my point. It's like you're looking for a needle in a haystack. And
Well,
so,
I guess
I mean, I'm
what
looking
I'm
for an
saying.
exact answer, and it's just not getting it. But
Well, the whole thing is this. When I said this is not the only way, I'm not saying that. What I'm saying is you can use that other technique, and it's called Ronskin. Okay, it's called the Ronskin, and you can use all of these functions. Okay. Uh, in fact, let's just do that real quick. Remember, determinant of the Ronskin. Okay, with these two functions, if it does not equal 0, then it's linear independent, okay? So here's f1, okay? And here's f2. And remember, you take derivatives of these, right? So here's the derivative of this one, and here's the derivative of this one. Then you take a determinant of this. So what it's going to be is it's going to be ln x times e to the x minus 1 over x e to the x. And this does not equal 0, okay? That we're going to try to show. So e to the x can be kind of dismissed because we all know that doesn't equal 0. So now we have ln x minus 1 over x does not equal 0, and then we need to show this, okay? So showing this is a little bit more difficult, okay? Because remember last time we did the Wronskian, but we got like 6, right? We got like a number, right? Here we didn't get a number. So you have to show that this function, okay? Yeah, okay, you have to show that this function, ln x minus 1 over x never equals 0. So actually, everybody give me a second. Let me graph that real quick in my graphing calculator. So when there's x's in the in the final result of the determinant, it's a little bit more, you know, involved than just a constant. Okay. So let me type this in and just see what we get. And we all know the answer. The answer is linear independent. But let me just graph this.
So I guess the ultimate answer for all these problems is when in doubt, 0. C1, C2 equals 0.
Well. Okay,
Or
hang on.
C3, C4, C5, C6, C8, C9.
Okay, hang on. Okay, this is the graph of ln x minus 1 over x. It looks like this, okay? So, actually, yeah, whatchamacallit. So the thing is that I'll have to think about this one, okay? Because it does equal 0 at some point. So what they're probably going to do is they split it up in an interval. Okay, they probably split it up in an interval, and they probably say at some x value, as long as the function, as long as the x values in the function are bigger than this, then it's probably true. So let me think about this and get back with you on the proper explanation, because again, when you have x's in here, it makes it a little bit more difficult. But we're saying this function doesn't equal 0, and it actually does, but see, it only equals 0 at one point. Okay, I think that's the whole thing, okay? So I think the answer for this is it's linear independent, right? Except for this, except for the one x value right here, okay, where the graph is, and it's not linear independent there. But overall, it is linear independent, okay? So yeah, so it gets a little complicated, but I guess what I'm trying to say is this finding the c's is not that bad. Remember, just look to see if it's a constant multiple. If it's a constant multiple, then you know you're going to find c's that are not all 0. If the functions have nothing to do with each other, then probably all of the c's are 0. Anyway, and if you don't like using this technique, then you can use the Wronskian to try to figure out if you can determine linear independence or dependence based on Wronskian, and then you know, that's an alternative. Okay. So next one. Okay. What if I gave you something like this? So we have y1, we have y2, we have y3. Okay. And we're supposed to show that this is linear independent. Okay. But we're going to use the Wronskian determinant. Okay. Okay. So here's the thing, okay? We all know how to take a determinant of something that is like 2 by 2 matrix, right? A 2 by 2 matrix, it's easy to take the determinant. 3 by 3 is also fairly easy, but when you start getting into like a 4 by 4 or 5 by 5, it's like it's not fun, okay? So like 2 by 2, that's doable. 3 by 3, that's doable. Anything higher than that is a little bit more involved. But anyway, we're going to go over how to do this, okay? So when you evaluate this Wronskian determinant, okay, you're going to put all three functions here, okay? There's all three functions. And remember, underneath these are derivatives, right? So derivative of e to the x, oh, it's just e to the x, just e to the x. Derivative of this, it's going to be 2e to the 2x, and then 4e to the 2x. So all I'm doing is taking derivatives all the way down. Here, 3e to the 3x, and then 9e to the 3x, okay? So can anybody tell me, how do we take the determinant of a 3 by 3? Does anybody know any tricks or whatever? It's kind of complicated. There's a couple different ways, but I'm going to show you one way that I think is the easiest. Does anybody just know off the top of their head? Yeah, okay. So somebody said break it down into 3 2x2s. Actually, that's correct. Okay, finding these determinants, there's like lots and lots of techniques, okay? So like one technique is like writing this out 3 different times and doing special things to it. But anyway, I'm actually not gonna do that. I'm gonna try to convince you, okay? Let me try to convince you to do it my way, okay? If you want to do it another way, that's okay. But anyway, I think this is the easiest way for a 3 by 3. Okay, the first 2 columns, okay? The first 2 columns in our determinant, we're just going to write these again, okay? We're going to write these again. So we have this. So you basically repeat these, okay? Then we're going to do this weird multiplication thing where we grab these 3 together, we add them to grabbing these 3 together, and then we add them grabbing these 3 together, okay? And let me think here. When you do this, okay, if you make these groupings of diagonals, these in particular are going to have negative signs on it, okay? So you're going to multiply all of this, okay? So you're going to get negative e to the x, 2e to the 2x, e to the 3x, okay? So that was the first row right here. Second row is this, and we're multiplying all of these, okay? Second row is this, okay? And then the third one, the third diagonal is this, okay? But we're not done, okay? Now what we're going to do is we're going to take another row of diagonals. We're going to take this row right here, okay? Then we're going to take this row right here. And then I'm going to take this row right here. I'm going to add these. So everything in green is going to be a plus. Okay, so I have that one. Then I add the next diagonal row. Then I add the next diagonal row. Okay. So if you take all of these, right, if you take all of these and you basically combine all the terms, okay, what you should get at the end of the day is this. You should get, if you add all of this up, 2e to the 6x, and you're trying to set this not equal to 0. So in other words, basically you're just taking these weird diagonals, and so you don't have to memorize really any formulas or anything. The only thing you have to remember is when you have a diagonal that looks like it's increasing, going up, that has a negative, and the diagonals that go down have a positive. That's all you have to remember. So I like this technique because I don't have to remember any formulas. Okay, so if you combine all of these, it's a little tricky because when I first did this, I didn't multiply it outright. But anyway, you should get 2e to the 6x, and the e to the 6x, we all know that that never equals 0 because remember, exponentials have a horizontal asymptote, at y equals 0. Y equals 0, you have a horizontal asymptote. Okay, so what happens is that the e to the 6x term, that just goes away. You can omit it. And so now you have this. You have 2 does not equals 0, which is true, right? And that shows linear independent, okay? So, so you can show linear independent or dependent by using the previous basic methods of writing out the definition and trying to find the C's, right? You could use that, or you could use this Wronskian determinant and try this. So there's different ways. Okay, so any questions over this? So look up determinants on the internet or in your book or whatever, and
Can you go over
look
that?
at them because, yeah.
So basically, we were doing the bottom from the top, like from the red and the green, and that's how you're getting the 2e to
Yeah,
6x.
exactly. So
Okay.
so to sum this up, you have this determinant, you fill it all in, right? Then you expand the first two columns and just rewrite them, okay? And all that
So
is
you're
doing is that's
okay. So you're
just
just
basic setting
yeah.
something
So
up.
all the e's, yeah, for like everything on the left, the e's cancel out, the two e's cancel out, and we're left with 9e to the 3x, and then so the middle, the 4e's. So you're left with just I don't know where you're. Is that you're just left with 4 on that, or -3
Okay,
for the
so
middle one?
basically these groupings of 3 and the diagonals. The diagonal groupings, you're multiplying all those together, and the ones in red, you put subtraction signs in front of them. The ones in green, you put addition signs in front of them, and then you have to add and subtract all of these together to get a final,
And and
final,
and, that, and, that's, and that's what I'm trying. That's what I'm trying to follow you. X.
okay,
That's
so the
that's what.
thing is that to get to the 2e to the 6x, that might take like 5 or 10 minutes, depending on how fast you are. So I would say that as like an exercise after the lecture. After the lecture, see if you can simplify all that to get 2e to the 6x. Because it's not easy, because it's easy to make mistakes. And when I first did it, I made a mistake and I didn't even get the right answer. I had to do it twice to get it.
Okay.
But if you do it right, it will simplify to 2e to the 6x. Okay, so that's how to show linear independent. And you can also show linear dependent too, because all you have to do is set this equals 0 instead of not equal to 0 to show linear dependence. When you set it not equal to 0, you're showing linear independence. Okay, so we're going to clear this and talk about more stuff. Okay, so consider this, okay? So here's some solutions, okay? And these solutions, okay, these solutions are the solution of this differential equation. Okay, so we have e to the x, we have e to the 2x, we have e to the 3x. These are all solutions of this differential equation. And if you look at this differential equation, this is third order, right? Third order, because it has a y triple prime in it, okay? And I don't think we've solved anything like that yet, okay? Anyway, okay? Knowing everything that we have gone through, okay? Also these solutions, okay? They're all linear independent, okay? So if you have solutions and they're linear independent, okay, and someone gives you them and they say these are the solutions of this, then how would you write down the general solution? Okay, so there's this concept called the general solution, okay, and it kind of has to deal with, remember how we talked about that idea called superposition, where you can basically chain several solutions together, because if one solution is a solution and another solution is a solution, then you can make like you can have like a multiple. You can combine those two solutions to make another solution. Okay. So there's this concept of a general solution. If you are given y1, y2, y3, and these are all solutions of a DE, how would you write the general solution? It's basically kind of what we've been talking about. Does anybody know? Anybody want to take a guess? Okay, so general solution is going to be this. You just take the first one, right? Add it to the second solution, and then add it to the third solution. Okay? This is called the general solution right here. Okay? Now, here's some other stuff, okay? Remember how we talked about, there's that concept called homogeneous, right? Homogeneous, right? We had one on the exam like that where you plugged in T's. I believe that in differential equations, the whole idea of homogeneous, there's different, that concept applies in different aspects to different problems, okay? Because in these types of problems, homogeneous means, do you have a DE that's set equal to 0, okay? So, you know, just bear with me, but this is how they describe it. So, if you have something like this, okay, and I don't know if this has anything to do with the homogeneous property of plugging in T's. I don't know if this is related to that or not. I have to look into it. But anyway, it's just a bunch of definitions. If you have a differential equation and it's set equal to 0, it's called homogeneous, okay? Okay. If you have a differential equation, okay, and it's set equal to something, okay, that is non-zero, where this is not equal to 0, then it's called non-homogeneous, okay? So just know that, okay? Because what ends up happening is you have these differential equations, right? If it's set equal to 0, okay, great, you have certain techniques to solve it, right? But if it's set to something not equal to 0, you might have a general solution, but then you add another solution after it, okay? So we're going to talk about that in a second. So what I'm trying to say here is a lot of times you're just adding solutions on top of solutions on top of solutions. You have 3 solutions. What do? You add them all up, you put constants in front of them, and you say, hey, look, here's a general solution. And then sometimes you even have more solutions, and you add them after the general solution. So we're going to talk about that. Okay, so if I have something like this, y equals C1, Y1, we have C2 Y2 plus, okay, Cn Yn plus Yp, okay? You might be wondering what this Yp is. This right here is the general solution. Okay? But this Yp, this is called a particular solution. And you usually have this, usually you see this pops up when it's non-homogeneous. Okay, so if you have something that's non-homogeneous, you might have this particular solution that pops up at the end of the general solution, and you just tack it on there. Okay, these are weird concepts, but just go with me. Okay. Also, when you see something that is in this form, okay, when you see something that is in this form, this form that we've been talking about, okay, we've seen this format several times here. This is called a linear combination. Okay, so if you see something in the book or you read online or something and they're talking about a linear combination, they're talking about this specific type of format where you have constants in front of your functions. Okay, let's do a new screen and then we're going to do some more stuff. Okay, so we're gonna verify something, okay? What if I said we have this particular solution? Remember, Yp is called a particular solution. We have this particular solution, okay? This is it right here, okay? Okay, this is a particular solution of this guy. Okay, notice how this differential equation, this is not set equal to 0, right? If it's set equal to 0, you're going to call it homogeneous. If it's set not equal to 0, you're going to call it non-homogeneous, okay? Okay. Okay, so non-homogeneous, okay? Okay, so how would you verify Yp as a solution? Okay, how would we do that? Somebody tell me. And we've done stuff like this before, so this is nothing new. There's no new concepts here. If I put this on the test and said, here's this particular solution of this dE, how would we verify this? How do you verify any solution in a differential equation? Yeah, take derivatives and plug in. Okay, so we have y equals this negative 11 over 12 minus 1 over 2x, okay? To find y prime, we just take a derivative of this. It's just this, right? Y double prime, oh, that's 0, and y triple prime is also 0, okay? And that's kind of interesting because it's like if you have any polynomial, right? If you have any polynomial where the degree is finite, okay? I'm assuming you can't have infinite degrees of polynomials. I don't know. That's an interesting question to ask. But the thing is that if you have any polynomial, if you take enough derivatives, eventually it basically goes to 0, right? Because every time you take a derivative, it decreases the degree by 1, right? So the first term becomes 0, right? The second one is also 0, okay? The third one is what? 11 times negative 1/2. Then we have 6 times this. Okay, great. And this is set equal to 3x. Okay, well, this one went to 0. This one went to 0. We don't have to worry about those. This is going to be negative 11 over 2. This negative makes both of these a positive. Okay. So this is going to be what? 66 over 12, right? Plus x over 2 equals 3x. Did I do that right? No, I didn't. I messed up, but I know what I messed up on. I didn't distribute the 6. Okay, common mistake. This 6, it goes right. So 2 goes in the 6 3 times. Okay. So I'm asking you guys, is this true? Did we get, is this on the left-hand side the same as this? Well, okay. This is a 3x, this is a 3x. That means that this needs to be equal to 0, right? So we have negative 11 over 2
The negative. I
plus,
think that 6 should be a negative.
the 6 should be, oh, no. Oh, it was a negative, but yeah,
It
it was
was, and then you went minus
yeah,
6y plus 6.
okay. The 6 was a negative, but these quantities were negative as well, so that the negatives canceled each other out. Does that make sense? So it
Yeah.
used to be a negative, but when we
Yeah,
inserted
I
this,
saw this, and so I just.
yeah,
But if
yeah,
you,
no,
yeah, negative,
the
negative is gonna be
signs are
positive.
correct. Okay, the signs are correct. Okay, so the thing is that I'm asking you guys this right here. Did I get it? Did I get the? Am I correct that we have 3x equals 3x at the end? All we need to show is that these guys cancel out right here. So does negative 11 over 2 plus 66 over 2, does that equal 0? Is that true or false?
It's true.
Yeah, it's true. All you have to do is just multiply by 6 or something like that. Or this was supposed to be 12. Multiply by 6, top and bottom, and yeah, it's true. So it worked out, okay? So what did we do? We just verified that this was a solution, okay? So here's the interesting thing, okay? This is the whole interesting thing about this, okay? If somebody wanted the complete solution, right? Complete solution, okay? Maybe I'll write this on the next slide. I don't have any more room here. So if somebody said, hey, write the total solution to this, didn't we just learn that we had this in our previous examples? We had this one, this differential equation equal to 0, right? And this one had solutions, right? This one had solutions e to the x, e to the 2x, and e to the 3x, okay? But then we also had the same differential equation Okay, we had the same differential equation, but we had, instead of 0, we had some other function, right? This was 3x, okay? So the full solution to the homogeneous one, the non-homogeneous differential equation, it's the general solution, okay, plus the particular solution, okay? So the full solution to the non-homogeneous differential equation is, you have your C1, you have your first solution, then you have your C2 times your second solution, then you have your C3 times your third solution. But remember, there was that other solution too, right? So then you tack that on, and that was the YP solution. Okay, so this is your general, and this is your particular. Okay, so what I'm trying to say is, when you solve some of these differential equations, if you have a non-homogeneous or a non-homogeneous, sometimes I say it different ways, if you have a non-homogeneous differential equation, a lot of times you will consider, you will set the right-hand side equal to 0, even if it's not. You'll set that equal to 0 and try to solve this to get the general solution first. Okay, then you will do other methods to get the particular solution, and then in the final end result, you're going to take your general solution, which is the solution to the homogeneous one, and then add it to this particular solution, which is part of the non-homogeneous one, okay? And this whole thing is your solution in general, okay? I know it sounds weird, but this is how it works. Basically, you're just adding solution after solution after solution. It's like every solution that you can find, you just add them all up to make one big final solution. It's weird, but this is how it works. Okay, so any questions over any of this? Okay, because we're done with this section now. Okay, section 4.1, we have finished this. Okay, so any questions regarding this section before we start on the next one? Okay, so no questions or anything. And by the way, we actually did not solve. We never, I'm just giving you the preview of what's to come. We never actually solved for the general solution or the particular solution. We were just given these solutions and we just verified them, okay? So in the future, you're actually going to be solving these like for real, okay? But in this case, I basically just said, look, we already know the solutions. This is how you write it, but you will eventually know how to solve for these, okay? All right, so let's clear this and let's talk about, we will jump into the next section. So this is section 4.2. Okay, reduction of order. Okay, so here's the thing. Let's say that we're trying to solve, okay? Let's say we're trying to solve this differential equation, but somebody was very nice to us and they gave us one solution already, okay? So we're trying to solve this thing and somebody already gave us one solution, okay? I'm going to show you a technique to how to solve this, okay? It's kind of complicated, but I think we can fit it in before the class ends, okay? But it's going to be kind of weird, okay? But just go with me, okay? Remember how we did substitution techniques, okay? Remember that? We did substitutions like Bernoulli and then like the U substitution, okay? Well, we're going to kind of do that, okay? But it's a different type of substitution. What it is the substitution is y equals u times y1, okay? Where y1 is a already known solution. So in other words, we're going to use one solution to help us find another solution, okay? So if we have a substitution, okay, let's just go ahead and substitute e to the x in for y1, okay? All right, great. Okay, so remember on those other substitutions, as soon as you have something like y equals something, if you're doing substitutions, usually you take derivatives of this, right? And then you plug it in, okay? So if we look up here, this goes up to y double prime, right? So that means that let's go ahead and take two derivatives of this, okay? And this is a product rule, okay? So the first derivative of this is going to be this guy. Okay, that's the first derivative. Second derivative, you have to think the second derivative is two product rules, okay? Because you're taking a derivative of this first derivative. There's a product rule right here and a product rule right here. So when you find y double prime, there's two product rules, okay? So the result of that, and you can verify mine, the result of two product rules, I'm simplifying it already because I've already worked it out, but you can double check and verify me, okay? This is the result. Basically, you take one product rule and then another product rule, and then you add all the terms together, combine like terms, you get this, okay? Okay, well, we have our y and we have our y and our y double prime, and that's all we really need to plug into this equation to try to solve this, right? So let's go ahead and do that. So I am going to take this one and this one, and I'm going to plug it in for both of these. So let's see what I get. If I plug in the y double prime, I get this. Okay, then I need to subtract it from my y, right? This I'm plugging in my y, setting this equal to 0. Then I notice that there's this term, and those go away. All right, so now we have this guy. And so then we try to solve this guy, okay? So if anybody can tell me looking at this, okay, looking at this u double prime e to the x plus 2 u prime e to the x, what do you think my next step is? Like what can I do with this? Can I do anything with this? Can I simplify it anymore? What can I do? Well, remember, if you have like e to the x or e to the something x, and that's set to equal 0, and that exists in every term, you can just take that out, right? Because it's never true, right? Since e to the x never equals 0, if you have e to the x in all of your terms, and that's set equal to 0, you could just ignore that, okay? So, so now we have this, u double prime plus 2u prime equals 0, okay? But here's the thing, okay? Here's the thing. Did that get us anywhere? Because if you look at the original DE, it's a y double prime minus a y, right? Well, here's u double prime like plus a u prime, okay? I mean, did we make it any better? Okay, well, this is what you're going to do. You're going to use another substitution, okay? And just bear with me on this. You're going to use another substitution, and you're going to let w equal u prime, okay? if you let w equal u prime and you take a derivative of both sides, you get w prime equals u double prime, okay? And what we're going to do is substitute that in here to change this to w's. So u double prime is now just w prime, okay? And u prime is now just w, okay? So now we have this, okay? And we will continue to solve this in the next one, okay? This is kind of complicated, but there ends up being a nice formula that you can use later on, okay? So you may not even have to use this technique. We will show that there's a formula that simplifies a lot of this. But anyway, this is still a valid technique. Okay, so we have w prime plus 2w equals 0. Okay, so let's clear this. Okay, so we have w prime plus 2w equals 0. Can someone tell me how to solve this? How do we solve this one? Okay, this is, since we did that other substitution, we took something from a second order down to a first order. So it's not that bad, okay? But if you look at this, this is linear, okay? Remember, linear, right? So linear means we have some y prime plus some p of x times y equals 0 or some other function. Do you have a question? Okay, so you can treat this as a linear dE. So you can say e to the p of x, which is 2 integral dx, right? E to the integral p of x dx. So this is just this, e to the 2x, okay? So then you can do the whole reverse product rule, where you have w times your integration factor, right? How to solve linear, okay? All right, so then we can move the dx over to this side, and then we can integrate, okay? So when we integrate, integral cancels with the derivative. We have w is e to the 2x, okay? And then over here, you have to think that there's an x here. This is like 0 times x, okay? So if you were to try to increase the power on x, you don't, because the constant is 0. So it ends up just being a c. Okay. So in other words, the variable, because there's a 0 on in the integrand, you just get a plus c. Okay. So then you can get something like this. Okay. W equals c times e to the negative 2x. Okay. But remember, okay, remember we had those substitutions, right? We had w equals u prime. Okay. So let's substitute that back. So we have u prime now is equal to c e to the negative 2x. Okay, great. Well, what do we do there? Well, u prime is just du by dx, right? Okay, so multiply both sides by dx, okay? We have du equals this now, but we're integrating, right? So let me just get rid of that. So when we integrate du, we just get u. And then when we integrate this, well, we just have, and I can call this C1 if I want. If you integrate this, if you integrate, this is just an interesting formula. If you integrate e to the ax, you have 1 over a integral, 1 over a e to the ax, okay? In other words, this is just a simple u substitution, and if you do it enough, you'll realize that whatever constant is in front of the x, you do 1 over that constant. So when you integrate this, you just do 1 over the constant in front of the x times the same function, okay? But then we add some other c, okay? We're going to add a c2. Okay, so where do we go from here? So, okay, here, let's wrap this up. Okay, we have a U, right? We have a U, and this is like our solution, right? But remember at the very beginning, and I know this is kind of complicated, but just bear with me. Remember at the beginning, we had y equals u times y1, right? Where y1 was the first solution, right? So all you have to do to get the final solution is take your u and plug it in here for this u, okay? So if you do that, you'll end up getting something like this. You'll get negative c1 divided by 2 e to the negative x plus c2 e to the x, and this is your final solution, okay? And this technique is called reduction of order, okay? And basically what it is you're trying to solve a DE, and you're given one solution, so you do some substitutions with that one solution that you already know to find the other solution, okay? But I think there's easier techniques than this. There's actually like a formula to solve directly for it, and we'll get into that next time. So yeah, that was kind of complicated, but that's just the nature of these types of problems. But this is how you do these. It's kind of weird, but just look over it and try to make sense out of it. Lots of substitutions. Okay, so that's really all I have for today. Okay, so in the leftover time, if you have any questions or anything, just let me know. So, does anybody have any questions?
Test is going to be is it going to be as difficult as the problems are concerned, or
I mean, well, okay. Here's the thing. You can always make things more difficult or always make things more easy. It's okay.
correct?
You can always do that. Okay. So I could take I could take the material in the first exam and then even make it harder or easier. The whole thing is that the next exam is going to cover. I don't think. I mean, I could possibly put something that we learned at the very beginning on the next exam. I mean, I could do something like that, but the whole thing is that for the most part, I will try to pick the new material that we have covered since the first exam, and that will show up on the second exam. Okay, and we will only have I will only put material on the exam that we've covered up to. Okay, so is it going to be just as hard? I don't know yet because I haven't made the exam. The only thing I can say is it's just going to have different problems on it, but it's going to be in the same format. Most likely there'll be 10 questions, they'll be worth 10 points each, and you'll have a week to do them. And also, here's the other thing. Like, I don't know if everybody has joined the Discord, because I think there's 8 people in this class, but I would highly recommend joining the Discord. That way you can ask questions and such, and even on the exam, if you are stumped on something, I can't just do the problem for you, but if you're stumped on something, okay, I can at least explain the concept, and I even encourage everyone in this class, if one student is stuck on
That's the problem with online learning. This is the one pet peeve I have about online learning is you cannot the tutoring sessions they're not really there, they're not really available, and you can't go someplace and then practice the homework if you have questions on some of the homework. And if you would post something, it would just take forever for somebody to get back with you online. And then I mean, this is why I don't like online learning at all. I mean, it's just ridiculous, but that's just my point of view.
Well, here's the thing. The thing is that I think we have to just make the best of the situation because I don't think there's an option to take this face to face. Okay, so try to work on some of the homework problems in the section. Okay, pick some problems that look interesting that are in this section or the last section. Okay, try to work on them. If you get stuck, post on Discord where you get stuck and the concept that you're trying to understand. And I would encourage you guys, I can always jump in and help, but I would encourage each and every one of you guys to help teach each other, because by helping teach one another, you end up learning how to do the stuff yourself. So work out some problems, post where you get stuck. And even if you're working on the exam and you're stuck on something, I can't help you with the actual problem, but I can help you with the concept. So that's there too. Also, also, if there is, I think I posted this somewhere, but there is a Discord for the Clear Lake Math Tutoring Center, and they have a section for DE. Okay. So I know that like this, it's kind of weird me referring to another school, but there's a Discord at U of H Clear Lake, a math Discord, and you can go join that one. And they have a section for DE, and they have DE tutors there. Okay, so but that's a different group than ours. Okay, but look on the internet, look up UHCL, University of Houston Clear Lake Discord Math Tutoring Center, and join that one and find the DE section and post questions in there. So there's an alternative right there. But yeah, the thing is that, and I will say this, I myself have taken some online courses, and if I have the option to take online or face-to-face, it's always face-to-face with me. I don't like online. But in this situation, apparently, the vast majority of all classes are online, so we don't really have a
Well,
choice.
I used to depend on the math center for all of the calculus that I took. And so, I run into issues with the homework, and then I just basically just circle them, go to the math center, and then they just help me figure it out. But so this is just completely different. And so you're basically sometimes you're hung out to dry on some of this stuff. And it's been a year for me since I've taken calculus. So it's
Okay,
trial by
well,
fire.
but here's
So,
but here's the thing. I am here to help you guys, right? That's my role, right? Is to help you. So if you are stuck, write what you're stuck on, post it in the Discord for this course, and then see if a student helps you. If not, maybe I might jump in. Okay, there we go.
all right.
So try that.
Okay.
And actually, anyway, I honestly okay, for this next exam, I think it'll be okay. Okay, I'm confident that you guys can do it. Okay. So anyway, these last two sections, look in the book, try to do some problems. You can also look on the internet. You can look on YouTube, look up some of these concepts, and then again use Discord. Um, so that's it for today, and basically we will continue more on this section of reduction of order. We are going to continue more of this next Monday. Okay, so have a good week. Have a good weekend, and see you Monday.